Hi everyone, my name is Robert Mijakovic and I will talk about the automatic selection of tuning plugins in the Periscope tuning framework using machine learning. The work is part of my PhD I did at Technical University of Munich under the supervision of Professor Michael Gernt. So let's start. In the picture above, you can see a heterogeneous system called Gyoku, a machine installed in Japan Agency for Marine Earth Science and Technology. This system consists of Intel Xeons coupled with PESI SC2 accelerators. Systems coupled with accelerators are not rare. 6 out of the top 10 biggest systems have them. Such large-scale machines help solve some of the greatest challenges humanity faces. Writing an HPC application for such systems requires extensive knowledge of particular scientific subjects and a good knowledge of the underlying system. So to use system resources efficiently, the application has to be carefully written and tuned, and that is time-consuming. On the top of that, the system changes every few years. The applications optimized for one system needs to be re-optimized for a new one. To support the tuning effort and automate the tuning process, autotuners are a must, and therefore in the scope of the AutoTune project, the Periscope tuning framework was developed. It is the first tool to bridge the gap between performance analysis and tuning and try to use it to improve the tuning process. PTF focuses on two objectives while tuning codes: to improve their performance and energy efficiency. It is a distributed tool that could, because of its hierarchical structure, scale on exascale machines and be capable of tuning programs with thousands or even millions of processes. It consists of the front end, which supports tuning plugins to control the analysis and tuning process, and the agent network. Plugins use the knowledge collected from the static program analysis, performance analysis, and the search algorithm to efficiently search the usually enormous search space in the form of tuning scenarios. Using performance analysis results, PTF can prune the search space and search only more promising regions of the search space. Each tuning plugin that focuses on a particular tuning aspect creates a sequence of such tuning scenarios. Each scenario consists of the variant, which is a combination of tuples of tuning parameters and their values. Each variant is applied to a specific region, and its effects is measured to a tuned region, which doesn't have to be the same. The third parameter of scenarios is tuning objective. For instance, performance or energy, which are two very important tuning aspects for HPC centers and for scientists themselves. The job of PTF is to find the optimal scenario or the optimal combination of tuning parameters and their values. PTF is distributed with plugins, with many plugins that optimize many different aspects, such as compiler flag selection, which finds the optimal combination of compiler flags and their values; MPI parameters, which finds the optimal combination of various MPI runtime parameters, for instance, when rendezvous protocol should be used; then dynamic voltage and frequency scaling, which finds the optimal frequency of CPU, and many others. But also it comes with an API, which allows users to write their own plugins that concentrate on tuning aspects of their interest. Now, to further automate the tuning process and make it more time efficient, we developed an approach that combines a set of tuning plugins and guides the tuning process according to tuning potential of each individual program it tunes. The most intelligent part of the approach is that it focuses on the most fruitful tuning aspects by predicting the tuning potential of the program it tunes from the unique program signature. Contrary to traditional approaches, It does not rely on so-called white box signatures, but rather on black box ones. The white box signatures expose the internals of the aspects they tune, but also differ for each of them. So each aspect has its own white box signature and are considered to provide better predictions than black box ones. On the other hand, black box signatures are not that well known for their good predictions and are not as extensively studied in previous research, but can be made generic for all tuning aspects. Our approach is unique since it uses the sensitivity of the program being tuned for a specific tuning plugin. We use the sensitivity of a program to carefully identify signature scenarios and discover its tuning potential. With the knowledge of tuning potential, we can focus tuning effort on the most fruitful tuning aspects. Knowing tuning potential before actually applying tuning plugins. For instance, if by applying the MPI parameters plugin, we could improve performance 2 times. With the DVFS plugin, improve performance just by 15%, and with the CFS plugin 3 times, we could focus first on compiler flags, followed by MPI parameters, and completely ignore DVFS if 15% isn't worth time and effort. Now, I will tell you more about the approach of the adaptive sequence meta plugin, or a plugin that combines other plugins. As every machine learning approach, this depends too on knowledge collected in the past tuning processes. The approach is split into 2 phases. First, of course, for machine learning training, and then the second is tuning. The training process starts with the identification of signature scenarios, which are the best characterization of the search space as possible, and crucial for good prediction of the tuning potential of program. Once the signature scenarios are known, the signature scenarios and tuning results about the past tuning events can be fetched and used to train the predictor and create the prediction model. With these 2 components, the signature scenarios and the prediction model, we have both components that are actually necessary to do tuning. When the user requests tuning, he selects an application that he wants to tune. The application is given to PTF with the configuration set by the user that contain his expectations to justify the tuning effort for individual tuning aspects and which tuning aspects has to be tuned for. The application is now executed with several signature scenarios, and the signature is created. The signature is now used as input to the prediction model to predict the tuning potential. Depending on the mode the meta plugin was configured for, we either use the predicted numerical value of the tuning potential to determine the most promising plugins, or classify the given program as having high or low tuning plugin or low tuning potential, and decide whether to apply the plugin. In case the meta plugin is configured to predict actual tuning potential for individual tuning plugins, it can order them according to their tuning potential and start applying ones with the highest potential first, followed by the ones with lower potential, until the user specified time budget is spent. The other mode of operation predicts the tuning potential numerically for each plugin, so-called regression-based classification, and apply tuning plugins with potential above the user's specified minimal improvement, or simply tuning plugins that are classified to have sufficient potential. Once the tuning plugins are applied, the tuning results and signature is stored in the historical tuning results database and used to improve the future tuning efforts. To better understand the approach from the previous slide, I will now give a little example with the CFS plugin. First, we start with the identification of signature scenarios. In this example, the user has decided to tune compiler flags with only three flags, with each with several possible values. This results in the given search space. The signature scenario identification now finds out that 4 scenarios from the complete space are sufficient to well predict the tuning potential of an application. So let's imagine that these 4 points. For that, we need to run the program with these 4 scenarios, and based on their execution time improvement, the prediction of the tuning potential can be made. For instance, from the run with the first scenario, speed up of or slowdown of 0.85 was achieved relative to a reference scenario. Or for a reference scenario, let's imagine that it was 0.2. Okay, for the second one, it's 1.07, and so on. The signature that consists of 0.85, 107, 4.12, and so on is given to the predictor, and the predictor can make prediction of the tuning potential. Based on the signature or sensitivity to the search space, the predictor can now predict the tuning potential, for instance, of 6.5 to be expected. Depending on the user expectations, the program could be classified as a program with sufficient tuning potential, and therefore the CFS plugin could be applied to it or not. Also, the predictor is capable of classifying the tuning potential of the program to be significant or not, again depending on the user's expectation. So now I will explain 2 techniques used for signature scenario identification. The main challenge for signature identification is to find the set of minimum size that provides as good as possible predictions of the tuning potential of applications. Evaluating each scenario can take significant amount of time, and therefore we want to evaluate as little scenarios as possible, but make an overall prediction as good as possible at the end, and not to tune applications whose tuning potential is too low, which is very expensive in terms of time. We have evaluated 2 methods, one based on entropy, called information gain, and one based on clustering, k-medoid clustering. You might have heard about the information gain, as it is used in decision trees and basically measures how much information a scenario carries about the search space. The method removes scenarios one by one and calculates how much entropy was lost. Entropy stands for amount for a basic quantity of information. The first n scenarios with the most information are kept, while others are removed from the set of signature scenarios. The next method is k-medoid clustering. Here we create clusters of scenarios and assume that their medoids over here in red and in gray hold enough information about other scenarios from the same cluster that it is not necessary for them to be evaluated. So once we know how much information each scenario brings, we have to decide where is the sweet spot between having more signature scenarios and better tuning potential predictions, and where we are just wasting time. To achieve this, we have employed the elbow method, where the decision is made based on the point with the highest change in the slope of the cost curve. With every additional signature scenario, the cost reduces. As it grows, it reduces, and however, each new scenario, signature scenario, reduces it less and less. Therefore, we select the first n scenarios with the highest influence on the cost and stop at the point where new scenario stop bringing a significant reduction. In the graph, we can see that the cost for the signature size of 3 is roughly 550. With the size of 4, it drops to significantly to 330, and with 5, it drops further to 230. But as we increase a number of signature scenarios to, for instance, 6, it drops very, very little to 210, and then with 7 it drops approximately to 200. And for that reason, the optimal number of scenario is selected as 5. On top of that, we slightly penalize a too small or too big number of signature scenarios. The next important component is the predictor, which predicts the tuning potential from the application signature. The predictor supports 3 modes of work. First, the classification, which labels programs to have sufficient or insufficient tuning potential. The second, regression, which predicts what is the actual tuning potential, for instance, 50%. Regression, then the third one is regression-based classification, which predicts the tuning potential, and based on the tuning potential classifies the program to have sufficient or insufficient tuning potential. The predictor is based on the support vector machine algorithm, so a traditional algorithm, and its selection is dictated by the size of the dataset and its ability to generalize. Due to dataset size, deep neural networks were not an option, but rather more traditional methods such as shallow neural networks and SVM. The next challenge is which kernel to select. There are several kernels available with the SVM library, such as linear, polynomial, radial basis function, and sigmoid. As it was not very clear which one best suits our dataset, we have decided to evaluate them all. So, to create machine learning based predictive models for programs tuning, we depend on historical tuning results from previous tuning efforts or processes. In machine learning, having a more high quality data is always beneficial. Good models depend on data that well represent workloads that are used in HPC sites. Therefore, to train and evaluate the proposed methods, we have used datasets collected on a wide range of benchmarks from benchmark suites of leading US agencies, laboratories, and their collaborations, such as NASA, Argonne National Lab, Coral, a collaboration of Oak Ridge, Oregon, and Livermore, Lawrence Livermore National Lab, Los Alamos National Lab, and the Manteva project. The data was collected while tuning the benchmarks with PTF on 500 randomly selected scenarios from 2 plugins executed on SuperMOOC, a supercomputer LRC. The data was collected for more than 2 months. 2 plugins are CompilerFlex Selection plugin and the MPI Parameters plugin. Each plugin has its own set of applications. CFS with 52 applications, and MPI Parameters plugin with 35 applications. The resulting dataset is 26,000 points for a CompilerFlex Selection plugin and 17,500 points for MPI Parameters plugin. For 2 classification methods, the pure classification and the regression-based classification, we have evaluated them on both plugins. To measure the accuracy of binary classification, we could use accuracy, recall, etc. Imagine you have a predictor that predicts cancer for patients. Your dataset contains 95% of samples for patients without cancer. You have a bogus classifier that always predicts that patients don't have cancer. The accuracy of your predictor would be very high, 95%. But does this predictor is useful? I don't think so. I would say that it is useless and misleading. Therefore, as a metric to quantify how good the predictor is, we use a metric that doesn't suffer from this problem, and the metric is called F1 score. The classifier accuracy is represented by a box and whisker plot, where the box represents the first and third quartile of the F1 score. The line inside of the box represents the median F1 score. The whiskers represents extremes, or the minimum and the maximum F1 score. As you can see, CFS has very good F1 score for both pure classification and regression-based classification. On the other hand, MPI parameters plugin has somewhat lower F1 score, which could be attributed, in both cases, which could be attributed to lower dataset size, 35 instead of 52 applications. And for both plugins, regression-based classification has superior prediction. So and I just remember that I forgot to mention that one means perfectly done classification, while zero means that none of the predictions was properly done. So the main goal of this work was to predict the tuning potential early and avoid wasting time on tuning applications without significant tuning potential. Therefore, we showed the results for the CFS plugin with respect to the save time, but also to the optimal parameters being used for the kernel, for signature, and for the mode of work. So we have created several settings. In the table you can see these settings that artificially split the dataset into classes of applications according to tuning potential relative to three scenarios, 24, 96, and 6. The first two settings split the dataset the first setting split the dataset to 6 applications to be tuned and 46 not to be tuned, or other way around, 46 applications to be tuned and 6 applications not to be tuned. The next one splits the dataset into equal chunks, so 26 applications to be tuned and 26 not to be tuned. So, and this threshold is artificially introduced to make such a separation of the dataset. As we can see, the radial, the best kernel for this for CFS was almost always radial basis function in 5 out of 6 combinations, and only in one setting polynomial kernel was better, but it was really minimal advantage over the RBF kernel, also in this case. And then the best identification process for signature scenarios was almost always information gain, except in the setting number 4, where k-medoids was again better, but just by a little fraction. While the regression-based classification was shown also that to have the best results, except in the first combination where the pure classification was better. But I would, in reality, really suggest you to use the regression-based classification, or to use the regression-based classification. So on the right side, now we can see how much time was saved by using the proposed approach. Time necessary to tune all 52 programs is more than 770 hours, and it's marked in gray on the graph. Save time is marked by blue, and that is the time that would be spent on tuning programs with insufficient tuning potential if the method wouldn't be used at all and all programs would be tuned. The wasted time marked in red is time spent on tuning programs with insufficient tuning potential, plus time to evaluate signature scenarios of programs that are wrongly classified as programs with insufficient tuning potential. As you can see, due to its high quality of predictions, most of the time that would be wasted when all programs would be tuned is now saved. Okay, so now let's see the performance of MPI parameters and the time it's saved that's saved by using it. So this slide showed the same metrics as the slide before, but this time for the MPI parameters plugin. Again, as you can see, RBF kernel is the best performing, while the best signature identification method is information gain in all cases. and mostly regression-based classification provided the best results. Also, you can see that a very significant amount of time is saved, which would be wasted otherwise. The predictor had a harder time predicting for the first set first setting, sorry, and this affected the program whose tuning takes a considerable amount of time, and thus wasted time is quite significant in this case. But as you can see, in all other cases, very little to no time was wasted. Okay, so now let's discuss regression quality. To evaluate regression quality, we have used two metrics. One, root mean absolute error, and root mean square error. Both metrics do not take into account the error direction, which means that positive and negative errors do not cancel out. Which otherwise, if we wouldn't use such metrics, and use instead metrics that cancel out, we would get a wrong impression about the regression prediction quality. As we can see, both plugins have very small error, with MPI parameters having slightly smaller, with slightly higher extremes. As you can see, the whiskers are quite far away from the box. This is somewhat surprising, since the MPI parameters plugins show more significant problem with classification compared to CFS from few slides before. Okay, so then let's come up with the conclusion. As we can see, contrary to popular belief, black box signatures also can quite pretty well. Also, this work shows that using information gain is superior to k-mediates to detect signature scenarios, as they are capable of providing better predictions from smaller signatures. For classification, we can see that the best kernel is radial basis function kernel, and is supposed to be used. And this kernel is characterized also that it requires short training time. CFS shows that the F1 score is between 0.9 and 1, which means that 90% of the samples are at least 90% samples are properly predicted, classified, and with very high average of 0.96. For the MPI parameters plugin, we see somewhat lower F1 score, which could kind of be attributed to smaller data set size. And as we mentioned, big data set size with good quality data is a must in machine learning. So having more samples in the database would probably also affect MPI parameters plugin to have better prediction quality. Okay, so and also if possible, regression-based classification should be used for classification. That means basically that having more data about classes is beneficial for classification. So and also, as observed, significant time can be saved by meta plugin predictions. Okay, for regression, in the regression we can see that the best kernel is polynomial or linear, if we take into account training time. So polynomial kernel is slightly problematic because it takes significant amount of time to be trained, and linear and if we take into account also training time, I would say that linear kernel is also very good and probably the better choice if you want to minimize the training. Okay, so the predicted speed up of had low error of 11.85%, which is looks at the beginning quite big, but I assure you that This is not really a big error for regression. So and that is for CFS plugin, and it's even lower for MPI parameters plugin of 7.18. Yeah. So thank you very much for your attention, and please, if you have any questions, send them to me on the email written about this scratching monkey's head. Thank you very much, and have a nice day.